Now that we've gotten a handle on how to apply F equals ma in vector form to develop equations of motion, we're going to start introducing alternative forms of Newton's second law, which have some applications in specific categories of problems. So here we see F equals ma expressed in terms of linear momentum. And this definition mirrors what Newton wrote in Principia, which was saying that we have this motive force is equal to the change in momentum of an object. A couple of important things to point out about momentum that we're writing as P of P with respect to O as observed in the inertial reference frame is that this vector linear momentum is a vector, and we always need to write it as a vector. And then we also need to denote from what reference frame it's observed, because linear momentum is based on the mass, which is a scalar, multiplied times a vector, which is the time derivative of position. In any time derivative, we need to denote the reference frame in which it's observed. So now let's start rearranging this form of F equals ma into something that's useful for us. So we'll take our force, F sub p, we're going to multiply it times dt. So we're just taking our dt and moving it to the left side. And this leaves the differentiation of m sub p times our velocity, p with respect to o, as observed in the inertial reference frame on the right-hand side. And so that gives us an integrating variable dt on the left-hand side and an integrating variable of dv on the right-hand side. So our boundary conditions on the left-hand side are t1 to t2, and on the right-hand side are the velocity at t1 and the velocity at t2. And so now leaving the left-hand side the same as our integral t1 to t2 of our force on the particle p, and then integrating this right-hand side, we get the mass multiplied times the velocity of p with respect to o as observed in the inertial reference frame at time 2, and then subtracting the mass multiplied times the velocity at time 1. And so we can rearrange the terms, and this is the most common form that you'll see this expression in, which we have the linear momentum at time 2 is equal to the linear momentum at time 1 plus the integral of the force from time 1 to time 2. What's helpful about this form is that we're saying that at time 1 we have a known momentum, a known linear momentum, and then we operate on this system using a force, and we're going to operate from time 1 to time 2. And so starting with a linear momentum, operating on the system with a force, you can now think about what Newton's second law is actually saying. We're going to end up with a different momentum of the system by time 2. So now looking at these individual terms, for our units of momentum, we have the mass multiplied times the velocity. So it's kilograms multiplied times meters squared. And then this is also equal to, if you look on this side, force is going to be in newtons and newton seconds. And so we can express this in terms of kilogram meters per squared or newton seconds. These are both the same thing. The second thing to see here that's important is that this force term, when we are integrating across time, it's best to have force as a function of time, and we'll explain that a little bit more down below. But one thing to consider as we're judging on whether to use this form of Newton's second law is if we have force as a function of time, oftentimes we have force as a function of the state. And so when we have force as a function of the state, that still means that we need to solve the differential equations, the second order differential equations, in order to get the force over the time. So if that's possible to do, that's a nice way to wrap that in, but you'll see in just a moment that it's primarily when we know force as a function of time or force as a constant is when this form is useful. So let's examine those three situations that you can use as guidelines for when to apply this alternative form of Newton's second law. The first of these situations is when the external forces, the net external forces acting on a particle is equal to 0. This may seem sort of like a trivial situation, but what we're saying here is that linear momentum is conserved. So P of p with respect to O. This is a vector as observed in the inertial reference frame. And it's the time derivative of this is equal to 0. So it's not changing. And so what this means is keep your eyes out for problems in which the external forces aren't changing. And when you notice that, then this form is a great form to use because it cuts out solving the differential equation. The second situation where this form of Newton's second law is extremely helpful is when we know the force as a function of time. And hopefully this is obvious from the expression, but if we know force as a function of time, we can integrate that over time, and then that gives us the relationship between our momentum at time 1 and time 2. Two common ways that this occurs are that when force is a constant, so that means there's constant acceleration on the system, or when we've measured force over time using an instrument like a load cell that's attached to the system to be able to get that information. The third instance where this alternative form of Newton's second law is really handy is when we have a really small time period and coupled that with a sufficiently high force. And this is called an impulsive force. The impulsive force we write as an F with a hat, so it's still a vector. We need to have from time 1 to time 2, and then this is going to be equal to the integral from time 1 to time 2, except what's implied here is that this force is going to be over a small time period. Now this is a special circumstance compared to our first and our second instances where this is useful, because generally when we think about the force equal to 0 or the force across time being known, that can be long time periods, it can be short time periods. However, when we reduce the time enough, then we consider this an instantaneous change in momentum. So let's work with a one-dimensional case in which if there's the line of travel that our particle P is on, and it can move in there's our positive x direction, positive x or negative x, as a function of time, then when we apply a force to this system, and the force being in the line of action, and it's an impulsive force from T1 to T2, then our impulse is going to be practically instantaneous. It does have an area under the curve, and that's how it's going to fit within this impulse momentum equation that we have here. But what we see here is that when we apply this instant force or this instantaneous force with sufficient magnitude, we get an instantaneous change in momentum. And so if we examine our curve here, x as a function of t, let's say that our particle P is moving toward the origin. As we see here across time, we're moving to 0. And if at 0 we apply an impulsive force that's in the positive direction, there is no instantaneous change in position. And we see that here because x is still equal to 0 at that time. However, when we take a look at our speed plot over time, we see that at the application of the impulsive force in the positive direction, we see an instantaneous change in speed from being negative to being positive. And so that institutes a change in speed, which is also a change in direction of the path. So we see a change in momentum. And with this, we're reinforcing the fact that momentum is a vector. When we apply an impulse, it can change either the speed or the direction, and we have both in a vector format. Let's say that we had taken our force vector, and instead of when it was at time, or when it was at position 0, applied it in the positive direction, let's say we had applied it in the opposite direction. Then our change in speed would have been in the other direction. It would have been in the negative direction for speed. That wouldn't have changed the direction of travel of the particle, but it would have sped it up. And so then we would find a steeper slope after that impulse was applied. So in that case, we have a change in speed, but not in direction. And so that's why it's important to write our equations out in vector form, and then to deal with all the directions using our basis vectors, using the tools that we've developed over the last chapter. Another feature of the impulsive force that we'll take advantage of is using this for boundary conditions. If you recall our boundary conditions so far in any of our systems, let's give an example of our simple pendulum, is that we've always pulled the pendulum back from a midline and then let it go. And so we've pulled it back to a particular theta, and then this is a position boundary condition in which we would say that we have theta at time 0 is equal to some given number. Let's say it's 45 degrees. And then our other boundary condition, because we need another condition for our state, is theta dot. And up until now, we've always said that theta dot, the initial condition, is equal to 0 degrees per second. Now we could always theoretically apply theta dot at time 0 to be something else, but we haven't had the physical tools to actually make that happen. But now we know about this impulsive force, which is applied at an instant in time. If we apply that at the instant in time when t is equal to 0, we've now effectively added a value, a non-zero value, for this portion of the state. Remember, our state is our position and our speed. We've typically done an initial position. Now we can apply an initial speed by inserting an impulsive force at time is equal to 0. So in summary, what we've done is we've developed an alternative form of Newton's second law as applied to a particle. And so the interpretation here is that if we know the momentum of the system, if we add the force over time, we can integrate that force over time and then come out with a new momentum. We've talked about 3 different situations where the external net force is equal to 0, where we know force over time, and then this last application, which is where the time in which the force is applied is instantaneous or extremely small, and then that defines what we call the impulse, or it's an impulsive force, and with that we're instantaneously changing the momentum from time 1 to time 2.